Yet again, we meet, Internet. So welcome to Delegation. So in this challenge today, I did have to do little cheatsies. Little cheatsy here, smiley face, acknowledging the cheat. But I did a lot of trial and error before I cheated, so I knew exactly how the attack occurred, why it did what it did, and I think I know why I wasn't able to actually get the solution that I preferred to do through a code instead of through the console. So we'll talk through all that stuff, but let you know that it's okay to cheat. I'm being vulnerable to you, Internet. Welcome. It's my mind. All right, delegation. With this challenge, there's a few different things, but really the goal here is to ensure that we can claim ownership, and we can see that stated here at the top. So the goal of this level is to claim ownership of the instance that we've basically pulled down ourselves. Now, below this, it states that there's a few hints here that might help you, one of which is the concept of delegatecall, a low-level function. Now, with this specific call, you can learn about this, but also there's mentions of fallback methods, so you need to kind of have an idea of what that is and why it exists and what it does, and then method IDs. And throughout this entire process, we'll talk about each, and we'll talk about a lot more than just that, but that's really the hints and the ideas of what you want to consume and kind of have a gist of. Below here, we have two contracts. So we have a delegation contract and we have a delegate contract. Now we will jump into the code in a second, but before we do that, I want to walk you through some resources that I found useful, and then we'll jump specifically into what a delegate call is, and then we'll talk about the code. So first things first, as I stated previously, I did do little cheatsies. So thanks to Web3 blockchain developer guy, his Ethernaut series has saved me quite a few times. So thankfully I was able to kind of follow along with him and figure out specifically the end solution that he created via the console instead of through code. So that was useful. Some other resources. I read an ungodly number of articles on delegate call, not just the attack itself, but how delegate call functions and then kind of the premise of it and all that stuff. And out of all of those, Sigma Prime, I feel like wrote the best explanation to the attack itself. And when reading through it, I kind of came across another explanation that was identical from the Mastering Ethereum book. And I'm pretty sure Sigma Prime may have copied and pasted that into their explanation. But hey, no judgment. I'm not sure what came first, the chicken or the egg. But those two are really good explanations, identical in nature. So if you like dark mode, read it in GitHub. If not, read it here. Same thing. But the key thing in this explanation, the reason I appreciated it so much, is that first they kind of explain the concept of delegate-call and the difference between delegate-call and call, because they're similar in nature, or at least they're two opcodes that sometimes get smashed together. In addition to that, they talk about the vulnerability specifically through an explanation of Fibonacci. So it's a Fibonacci library, and the reason I like this explanation is because it's somewhat more realistic. It's not necessarily a toy example that's somewhat small and minuscule, but it's pretty robust because they explain a few different methods of how you can exploit this and the impact of such. And if you read through this, you'll see that there's some explanations to the two contracts. So there's a balance and then there's an attack contract. But like I said, the best part about this is they actually go into depth explaining specifically what you're seeing in the code above and how that correlates to the vulnerability and the flaw within delegate call. They have an attack contract, obviously, and they have more in-depth explanations here. And they actually reference a real-life example, which is even better. They actually walk you through the code here, specifically what happened with that real-life example. And it was a wallet parody. Yeah, this one here, I think. Yeah, so the parody wallet multi-sig got hacked for $30 million. 300 million? No, it's 30 million. Maybe it was 30 million when it happened. Now it's 300 million. Yeah, here we go. 30 million. That's what it was. That's the number I had in my head. So that's a real life example of this specific attack occurring with delegate call. All right, those are two good resources. Some more resources I'm going to point you towards are, as per usual, probably the best YouTube channel I've found on smart contract development, period, just due to his ability to explain things in a very concise and meaningful way. So he has a two-part series on delegate calls and walks you through two different types of attacks, one simpler than the other, explaining the impact of both. And the code that he walks you through is linked here as well that I'll share. That specifically talks you through delegate call and a vulnerability for a contract called lib, hack me, and then attack. and then walks you through specifically. And this is actually a good explanation as well. So if you just want to read through the code, that's helpful. Another resource, and let me get the video as well, is this explanation here. So this is probably one of the first explanations I came across around the concept of being a delegate call being vulnerable. And the blog is okay, but I thought the video was better. So I want to kind of give this guy a shout out and hopefully get more people to view his YouTube channel. Is he actually explains the walkthrough of the attack here, specifically talking through delegate call and things like that. So that's another one I'll link. And with that being said, those are the main resources I wanted to share in relation to this specific attack. Now, let's get into the details. And if I close some stuff, we have some stuff around delegate call. So let me think through how I want to explain this. 1 second, internet. All right, I'm going to explain my notes before I explain the code, because I feel like if you understand what delegate call is, it's going to make the explanation of the code more intuitive for you. All right, so what is delegate call? Well, there's some great docs here. But in a nutshell, delegate call is basically delegating the execution of code for the state of my contract. And the best explanation that I could find is basically verbatim from this blog post here. Was it blog post? No, it was a Stack Exchange. So in the Stack Exchange, this person's explanation is delegate call basically says that I'm a contract and I'm delegating you to do whatever you want with my storage, meaning context or state. And you'll hear those synonymously discussed with delegate call. Specifically, context, state, and storage is all basically allowing the caller. So if I'm the caller and you're the callee, I'm calling to you to execute the code, and then you're going to execute that code on my context, my state, or my storage. Another explanation from the docs is less simple or intuitive. Is the code at the target address. So the target address that I'm calling is executed in the context of the calling address, which is me. Same thing, kind of what I just explained. And then context, another thing is when you read through this, you'll see that there's a few terms that come across that are such as variables that are going to be basically something that's going to be your state or your storage. The ordering of those variables are going to be very important, so we'll explain that later. The sender and the value are all going to be from that calling contract, so that's all going to be the same. It's not going to change as it goes from contract to contract. And here's a good explanation to kind of show the difference between delegate call and call, to kind of get an idea of what it looks like at a high level. First we have here is a call, so this is not delegate call, this is call. And with a call, you have your caller contract, right? So you have your externally owned account, so you're calling this caller contract. The caller contract's then going to call the target contract. As you're doing this, you'll see that the EOA address, so that human there, is associated to the sender and the value when you're calling the initial contract here. But when that caller contract forwards that on to the target contract, the sender is actually going to be that caller contract and not the EOA. The same thing applies for the value. So you're basically letting go of the context and you're giving the context to the caller contract instead of maintaining your own. But when we do this with a delegate call, when you're delegating that, you can see that the sender and value of the EOA address and sender value is all going to be maintained as we go through here. So as we call, the caller contract is going to maintain our sender address, and our value, and any of our state when they send that to the target address. And when they execute the code here, they're executing their code specifically on the context that we provided. So that's somewhat of a useful picture to get an idea of what the two are and how they're different. Let me see if I missed anything that was useful. No, did perfect, as per usual, internet. All right. Here we go. So we're going to talk about why is this useful. So why does delegate call exist? So delegate call exists for a few reasons, or at least a few of the reasons that I've found myself. There might be a ridiculous number of reasons, and I've just not found them, but these are the two main, most prominent reasons that a lot of people discuss. The original reason that I've come across is specifically for libraries, and you'll see this in the Solidity docs, and I think in Mastering Ethereum as well, where they talk about how the delegate call was kind of initiated or ideated around libraries, being able to create modular smart contracts. So you no longer had to basically rely on one smart contract being a massive contract, a monolithic contract. You could have like microservices for contracts, or something similar to when you're developing and you have a series of libraries that you're importing. And that kind of applies here. So if you want to basically delegate calls from different libraries into your contract, you no longer have to basically create all of this code here. You can just create the code here and then import all that stuff. And that was really the ethos of why this was created, so you could have reusable library codes. You didn't have to keep writing over and over and over utility contracts that do a similar function. Another use for this is actually proxy contracts. So this is for contracts that are upgradable, meaning that there's a simple diagram here that I wanted to explain basically what that is, and this is going to be a topic that I'll dive into in a separate video on its own, but really high level. You have a contract, and within the smart contract ecosystem, there are sometimes bugs, and there are features that you want to upgrade and things like that. In the traditional Web 2 world, we easily just upgrade our software and we roll it out, and you have a new piece of software out there. But with smart contracts, that's not as simple as a task. Here, the way to do that, or one of the ways to do that, one of the implementations of this is using proxy contracts, where you have your state sitting in your proxy, and then you have your execution code sitting in your implementation contracts. And if you have your old contract here that maybe has a bug and you want to upgrade it so your users don't get all their money siphoned away, you can actually transition. I don't know if it's a complete switch over or something you trickle over, kind of like a canary situation. But if you roll it over, you're going to roll over into this. So you can basically take your pointer that's pointing to this implementation of this contract and then point it to the new contract. So you have your bug and your bug's fixed and your users are fine. And that's one use of a proxy contract, or another use. One important thing I will point out here is, like I said, this is one implementation. There are some flaws in this implementation if done incorrectly. So Trail of Bits actually wrote this really good blog that I'll link, as well as the proxy contract blog from Open Zeppelin, who kind of popularized this whole process and concept of proxy contracts. And I'll point you towards both, so you can kind of get an idea of both ideas and which one, the trade-offs of both. There's not one better than the other, I don't think. And you can see that this Trail of Bits prefers contract migration over proxy contracts due to the fact that there's less of the chance of a flaw happening there. All right, so that's why it's useful, and that is why people use delegate call. Now, what's the flaw? What's the big mistake here? Why do people concern themselves or fear delegate call? Well, first things first is, as you've seen previously, delegate call in the Solidity docs that I pointed out is a low-level function, meaning that I'm pretty sure it's an opcode. So that's not as low as you can get, but that's pretty low. You kind of want to stay away from opcodes as much as possible if you don't necessarily know exactly what you're doing. Now, the way that we're going to basically take over our contract is a very simple exploit. So this isn't necessarily something that a lot of real world exploits have. The ones that we'll see real world wise are going to be this variation, but the way that we're going to exploit this contract is pretty straightforward, where we're basically going to use, we're going to gain ownership of delegate, which is kind of our goal, and we're going to utilize a middleman, which is delegation contract, and we're going to do that by making a call into that contract, and it's going to keep our state, allowing us to gain ownership. So this is a very simple method that we'll kind of run through together. But the traditional way, and the flaw that a lot of people run into, is actually the ordering of their variables, where you have a series of variables at the beginning of your contract, your state variables, and if you're going to delegate your state to somebody to execute that code, you need to ensure the ordering is the exact same. Reason being is that when you order your state variables, they're sitting in slots, memory slots, and they all start at slot 0 usually. And if we go down here a bit, you'll see some pictures that are useful to kind of intuitively understand what I'm talking about. So this example here has two contracts. There's a caller contract and there's a target contract. And here you can see they have a series of state variables. So we have value, sender, name, and call success. Now down here, we have some state variables as well. So let's not do that. Here we can see the same thing. So we have some address, so we have sender, value, name, and sender local. Now the important thing here to point out is that this one has value, sender, name. This one has sender, value, name. So you can see these are swapped, right? So the value is the first one, and here it's a second, and then sender is the first, and here it's a second. That's an issue. Reason being is that this value here is sitting at slot 0, this is sitting at slot 1, this is sitting at slot 0, and this is sitting at slot 1. Now these state variables are containing different types of data, and if you funk that up, basically, you're going to have an issue where the the attacker address could actually send in their address or some other manipulation to actually gain complete ownership of the target contract, and then they could siphon off funds or do whatever they want to do. And if we scroll down here a bit more, you can see the slot concepts. So here we have slot 0 for value, sender, and name. That's kind of the slot thing I mentioned. Here you can see a more intuitive understanding of what this should look like. So here we have the caller and target contract. Preferably, it would look like this, where we have the value in slot 0 for both, the sender in slot 1 for both, name in slot 2 for both. Caller success is okay because there's nothing here, so we're good with that. So this is what it's supposed to look like. But this is what it actually looks like, and this is kind of what I just explained. So we have 0 for sender, 0 for value, 1 for value, 1 for sender. That's an issue. Now, let's go to our code and explain the code. And actually, before I explain why that's an issue, let's see if we can get some example code to show you exactly why the ordering of those variables matter. And actually, I'm not going to explain it because that'll take too much time. So here's some homework for you, Internet. Go do your homework. The homework I want you to do is I want you to look at this specific code snippet, which is explained in this video series. So you can either watch the video series or look at the code snippet. But in the second video specifically, the smart contract programmer on YouTube explains the idea of what I just dropped to you. So the idea I gave you down here around the ordering of variables and how it's important to ensure that they're correct. In this video series, he'll specifically walk you through this code snippet and talk to you how basically in this code snippet we're going to be able to allow the attack contract here, the attack address, to become the owner and point its address to this lib so it can completely take over this contract. And the reason that happens is because the ordering is incorrect. Keep that in mind and watch that video, do your homework, and be a good student. All right, now with that being out of the way, let's talk about our own challenge. So in our challenge, we have some code here. And we're going to walk through the code, as always. All right, first things first. The compiler is .6 and it's floating point, so that is a no-no. Remember, we want this to be static when we put it out into production. So it should be, 8.0 with, no floater, just by itself. Below that, we have our contract for delegate. So this is the original kind of parent mama contract. And we have an address for an owner. We have a constructor, and the constructor is going to basically say whoever deploys this contract is going to be the owner, and we can put that there. Down here we have a function. This is my note here basically. And in this function, it's basically a pwn function. So if you're not much of a gamer, pwn is basically when you're getting owned by somebody. It's just like destroying in the video game. Fun fact, I think. And in this function, you can see that basically it states that whoever initiates this function, the sender will then become the owner of this contract. And that's going to be our goal. That's the key to winning this challenge. And that's why I've put this little note here. Now, in our delegation contract, this is going to be the second contract that's actually deployed, and this is the contract that we can interact with. The delegate contract above is something we cannot interact with because it was deployed prior to us getting the instance and gaining access to this contract, basically, or at least not directly. You'll see. Now, the delegation contract, we have another situation here, so let's look up here. We can see that they have the ordering of their state variables correct. So this is not going to be the flaw that we're going to be focused on. Ours is simpler, remember? So they're ordering correctly because this is sitting in slot 0, and this is in slot 0, so we're all groovy. Now for this, we're basically initiating the delegate contract above and placing it inside of this variable for delegate. We have our constructor saying whoever deploys this contract is going to deploy it to the delegate address. So we're going to ensure that this contract is then pointing to this contract up here. And we're going to place that address inside a delegate when we kind of initiate that contract and put it inside of the variable that we've initialized up here. And whoever deploys this contract, the sender will be the owner. So that's kind of the setup there. Now below this, we have a fallback function. Now if you don't remember, fallback functions, so both, let's say fallback and receive, such good handwriting. You should be so impressed right now. All right, so fallback and receive. Both of these functions exist for the reason being is that if you send message data or anything to a contract without specifically knowing the function that you're sending it to for that contract, then what's going to happen is whatever you've sent to that, it's going to go straight to that fallback or receive function. So that's kind of like a catch-all for a contract itself. That's kind of the high-level understanding of what a fallback function is. Now you can see this fallback function is external, and specifically there's a few things happening here. First is we're taking our delegate variable, so we're taking the address of the delegate variable, and we're actually going to do a delegate call on it, and we're going to send that data to that delegate. And we're going to basically say, okay, is the result true? If so, then if the result's true, then you're going to take it from this instance of this contract. Now, the important thing here is this delegate call, right? So we're delegating the call. That means that we want to take the state and the context of this delegate contract, and we want to run this message data through it, and we're going to execute whatever we want via that caller contract that we're calling to. Hope that makes sense. Now, I tried to create a bit of attack contract, a small attack contract to run on this, and I think now I'm just kind of making myself feel better right now, internet. So you're just gonna have to feel it out, all right? And the reason I think I couldn't get this to work is because I don't have access to the delegate contract, the address associated to that when it was deployed. I only have access to the contract for the delegation contract. So even when I do run my attack against this contract, I can't gain ownership, or I can't validate that I've gained ownership because I don't have access to delegate, I think. I don't know. Anyways, we're gonna do it through the console. Now that we understand what's going on here, what we're gonna do, I'm gonna show you a few steps of how we can solve this. So let's make this bigger. All right. So if we do contract ABI, we got to make sure that we're looking at the right thing. And here we can see that we have access to a few things. So we can see that we have access to the delegation and not the delegate. Reason being is we have our constructor here. If we open up the constructor, we can see that the input is going to be the delegate address, which lines up with the delegation contract here. In addition to that, we have our fallback function, which is specific to the delegation contract. So that's all groovy. And then we have our owner, which is the same as the delegate, the same state variable, basically. And if we do this, so if we go here, wait, and we call the getter for owner, we can see that this is currently the owner. So whoever that is the owner. And if we go to our setup here for MetaMask, you can see that's not us. So we are not the owner currently. Now, what we're going to do is we're going to create a variable that's going to hold the call we're going to make. So let me type this out, and I'll explain what it is. So it's a pwned attack, and we're going to do an ABI. Let me think about this. All right. So what we're going to do here is we're going to do web3 utils, and then we're going to do kakayak 256, and we're going to call pwn, the specific contract that we want to call. Now let's walk through specifically what we're doing here and why we're doing it. Now, I've created a variable mainly because I just want to have something to store all this stuff in so I can call it later on. And we're going to call the web3 library, which has a utils subset of libraries inside of that, and then have this hashing function. And there's a really interesting story if you're interested in knowing, if you want to know why they're not using SHA-3 instead of, so if they're not using SHA-3, they're using this. You should Google that, or at least read it in the Mastering Ethereum book. It's a really interesting backstory. And we're basically going to call the pwn function here. Now remember, the pwn function sits inside of our delegate contract up here. Oh, such good lined up right here. You can see everything perfectly. So I'm going to call this pwn function, and I'm going to put it inside of this. It's going to be hashed, and I'm going to put it inside of this variable. Now, the next thing is we're going to send a transaction to that contract with our variable. Now, to do this, you have to do it correctly and not incorrectly like me, so we need to put this inside of a data thingy. All right. Now, the reason we're doing this, and I guess I can push enter, so we're not waiting. Confirm. All right, back to the explanation. Now we can see here, there's a few things I'm doing. So I'm sending a transaction to the data section of the message data. So let's scroll this down so you can see what I'm talking about. Now remember what I said around sending stuff to sending something to a contract? So if we send something to this delegation contract and we don't call a specific function, so we're not calling a function inside of the delegation contract that exists. Remember, we're calling pwn, which exists inside of delegate, not delegation. And when we do that, this delegation contract is going to have its fallback function is going to kick into play because we're sending a function that's not existing in the delegation. So it's its catch-all basically. And when we send that data, we're going to send it via a transaction. We're going to send it inside of the data field. And this data field concept basically is pulled from Solidity docs. So if you want to know how to send a transaction inside of Solidity, there's a series of key value pairs that are associated inside of this send transaction object. So you should Google that if you don't really know what this is and why it exists. But this data piece correlates directly to the message.data item that's happening here. And we're going to send this contract here. Now, when we do this, when we send this data, let me pull this down. And actually, if you want, I can show you that, winner, winner, chicken dinner. Wait, you have to wait. So you can now see that 03D, 5, and that is us. So winner, winner, chicken dinner, we've owned this son of a gun. So what's happening here is we've sent this data, we've sent pwn here, and that's doing a delegate call, remember, on this contract. So we're going to send this item here. It's going to go through here. It's going to then call pwn. The sender is going to be us because we're doing the delegate call, meaning that we maintain, remember, the value, and we maintain the sender, as well as all the other state that we've provided. And that delegate call is then going to basically initialize this because we are the sender, so we become the owner, meaning that we are now the owner of this contract and we've pwned it. Now, that is it. Now we just got to submit this. Let's submit it. And congratulations, Ethernaut. We did it. We did it together. And here they basically link out to the specific attack that they discussed and how this was a real world thing that happened. Not the specific way that we've done it, but this specific weakness in delegation or delegate call. With that being said, Internet, I'll see you on Force.